I want to talk about free damp vibrations, and often these are the most challenging problems in the course because the form of the equation changes significantly dependent on what's happening, particularly with the overdamp case. Uh, this is a little bit, I mean, honestly, it's a little bit more involved than the force cases that we look at. So we'll solve some free damp vibration problems, look at the process, and what I'm hopeful that you will do is sort of recognize that there is kind of a recipe book associated with this. We need to set up the problem in a certain way. We need to get a result. Once we have that result, we then use that in some way to solve the rest of this. So consider the first example. I have two springs and a damper. So the damper is acting to slow things down, attached to mass A. Below mass A is mass B, which is attached by a string. And as you can see by the clever scissors, I'm going to cut it, and that will remove it from the problem. System is at rest when the cord connecting A and B is cut. What is the velocity of the system 0.1 seconds afterwards? Mass of A is given as 2.5 kilograms. Mass of B is given as 1.1 kilograms. K of the two springs is 185 newtons per meter. And C of the damper is 9.8 newton seconds per meter. So this is kind of a standard set of problems, and there's a reason why I've chosen these values, and I'll explain in a second. So if I look at the mass, I have a mass here that is undergoing forces that act to pull it back up, Kx, a retarding force that acts to slow things down, Cx dot, and I have weight, which is acting downward. Now, the one thing that you'll notice right away is that I have defined things as positive down. Downward is a positive direction. So if I do sum of forces in x, that's going to be mg minus kx minus cx dot equals mx double dot. And if I put in all the terms, I'm going to have the static term and the dynamic term associated with the spring. The other terms, x dot, when it's static, x dot is equal to 0, so damping doesn't occur, and when it's static, there's no acceleration. So really only the first two terms play a role. And in that case, those terms will go away. So my equation becomes mx double dot plus cx dot plus 2kx equals to 0. Put it into the standard form, and the only thing I got to recognize is that I have a set of springs that are in parallel, and you should be familiar at this point with series parallel solutions for springs. So it's 2k over m and c over m for those two terms. The natural frequency of this system is just going to be, using again definition, 2k over m square rooted. The critical damping coefficient, using the standard sets of formulas you've already sort of gone through and you should be familiar with, is twice the mass of A times the natural frequency, which is 60.83 newton seconds per meter. So this system is underdamped, and I already know from previous lectures that this is the form of it. X is equal to some constant d times the exponent e to the minus c over 2mt plus a phase lag associated with sine omega dt plus phi. If I take the derivative of that, I'll end up with this mess right here, but that mess only has an omega, the damped natural frequency, and it has the what amounts to the critical damping coefficients. So I have everything there. It's all sort of working out really well. Under static equilibrium, I already knew that this is x is equal to mbg minus 2kx stat, but I need to know that distance. So that tells me, first of all, where the system is before I put the mass B on. Then I have to add the mass B on there, so it's ma plus b minus 2kx ini is equal to 0, and that is the final stretch. So x ini is the distance from the static equilibrium position to where it is when it's released. So that gives me my initial conditions. My initial conditions then are going to be just x ini minus x stat, and it just starts from rest, so x dot is equal to 0. So putting those terms in and substituting into the first equation, I get x ini is d sine phi. For the second term, I get another set of equations, and I get rid of the d, and I end up with omega d cos phi minus c over 2m sine phi. And I end up with tan phi equals c over 2m omega d. If I substitute all the terms back in, I get solution, which is x is equal to 0.181 e to the minus 1.96 sine 12t plus 927 degrees, and x at 0.1 seconds is 0.05 meters. What would happen if you had a different damping coefficient, say 72 newton seconds per meter? Well, in that case, and I've kind of given the solution already, I know that the critical damping is still 60.83. I've calculated it before. X then has the form C1 e to the lambda 1t plus C2 e to the lambda 2t. System is overdamped, and we know that the form of the solution, and I know it, but make sure you know it, ma lambda squared plus c lambda plus 2k is equal to 0. So substituting in terms, putting all that together, I get lambda is equal to either minus 6.7 or minus 22.11. Substituting in for the initial conditions, x is equal to approximately 29.2 millimeters, and x dot at 0 is equal to, at t equals 0, I end up with the constants 0.042 and minus 0.013. Substituting them in and putting them in for time equals 0.1 seconds, I get x dot of minus 112.5 millimeters per second. Now that is an upward motion because of the axial system that I defined in this problem. Second example. This is a rigid body problem, so a little bit different. I have on the left-hand side a spring, on the right-hand side a damper, and at about the 2/3 mark from C to B and 1/3 from A to B, I have a pin where the entire slender rod is oscillating. The rod is in a horizontal position when it's in equilibrium, and the distances are given as A and 2A for the two things. Shouldn't be a surprise. I expect I'll be using a moment, and I will be stuck making use of my 1/12 ml squared rule. So if I just do a static solution and just let it sort of slide and see what happens, I have the spring force, which will be acting to pull it back down, and I have the weight force, which will be acting to pull it down. Now, they're on opposite sides of the pin, and because of this, they end up with force at A being mg over 2. Okay, so we got that. Static displacement and adjusting for sign, it's just Fa over k or mg over 2k. If I go a bit further and substitute in all the terms, I can sort of say, well, first of all, I've got a weighted term on the left-hand side. I have the static equilibrium term that corresponds to that, and it's going to go A cos theta, but the number is going to be the same. And so these two terms are going to go away. The terms that remain are Ka theta, A cos theta, and then the other one is 2Ca theta dot 2A cos theta, which equals minus Ma squared theta. And those are the final terms in there. So I got to recognize the spring force. I've got to recognize the dash pot, the damper, and finally I am going to put negative for a reason so that I have the correct signs in my equation. So I'm going to assume that it's just sort of going like this. V for this system where the damper is acting, because it's a function of velocity, is going to be 2A theta dot. So that's where I'm getting all these terms. So substituting in terms, Ka squared theta cos theta 2Ca theta dot 2A cos theta equals minus Ma theta double dot, I end up with this expression right here, which is K theta plus 4C theta dot equals 0. Equals minus M theta double dot. Canceled a whole bunch of A's there, simplified the equation, and everything sort of worked out reasonably well. Cos theta is approximately equal to 1, so I'm getting away with that. And my final expression is this one right here. And my natural frequency for the system is omega n squared, which is k over m. Same one as I'm used to, but it's not going to always be that way, so be careful. If I continue and just substitute in the terms, I have 4C over M, K over M, critical damping coefficient is going to be 2 square root K over M. And for the system shown, the equivalent damping coefficient, C equivalent, is 4C. For the system to be underdamped, which is kind of one thing I might want to check, C equivalent had to be less than CC. So put 4C is less than 2 square root Km, which I've just calculated. And C is less than 1/2 square root of Km. These are a couple kind of interesting problems looking at damp vibration. Understand how they're done, understand the procedure, and understand to a large extent, we're not asking for a lot from these. You just need to know the procedure. If you look at the crib sheets, if you look at what we've provided in the lectures, the solution sort of program, the solution recipe, is right there. Make sure that you understand how to apply it. And also understand what you're checking for before you put in the solution.